Picture a rocky planet where the surface never solidifies. About 41 light-years away, an exoplanet called 55 Cancri E orbits close to its host star that it is enveloped by a permanent, churning ocean of magma. It represents an absolute thermal limit for a rocky planet. On the opposite end of the extreme spectrum is the gravitational limit of a black hole. Here, matter is packed so densely that the resulting gravity pulls in everything around it. Past a certain point, even light is swallowed completely. We have a deep urge to know what happens inside these extremes, but we run into a physical wall. The core of a lava planet is hidden beneath the blinding glare of its star and miles of molten rock. A black hole singularity is shielded by an event horizon, the exact boundary where light fails to escape. We simply cannot look inside. For decades, the only way to model these hidden interiors was through pure mathematics. Physicists relied on the equations of general relativity to guess what might be happening beyond the veil. That approach is changing. Instead of trying to pierce the veil and look directly at the center, astrophysicists are focusing on the immediate perimeter. They are analyzing the violent, chaotic layers of matter fighting to survive right on the edge of the abyss. The environment immediately surrounding these objects is highly reactive. By studying how gas and light behave right before they are consumed or boiled away, we can calculate the exact properties of the invisible core pulling the strings. A supermassive black hole can hold the mass of millions of suns, anchoring entire galaxies. The void itself is invisible, but the space immediately surrounding it is a massive storm of infalling matter. In 2019, the Event Horizon Telescope collaboration captured an image of the supermassive black hole in the galaxy M87. For the first time, we had direct visual proof of this boundary layer, a glowing ring of radiation surrounding a dark shadow. That ring is part of an accretion disk. As gas and dust are dragged toward the event horizon, the particles pack tightly together and rub against each other. This friction generates intense heat, turning the matter into a glowing plasma. Right at the innermost edge, before matter crosses the point of no return, it enters a plunging region. The plasma accelerates to near the speed of light, releasing so much energy that it can form a quasar, one of the brightest objects in the universe. Because we can observe the speed and temperature of this glowing plasma, we can run the math backward. The behavior of the disk directly reveals the three core metrics of the black hole hiding inside: its mass, its spin, and its electrical charge. The accretion disk converts the unseeable physics of the void into a readable signal. Its motion and heat are the direct, measurable results of the singularity's mass and spin, effectively exposing the properties of the darkness within. We can apply this exact same observational logic to the thermal extremes of 55 Cancri E. This world is tidally locked, meaning one side constantly faces its star, baking under temperatures high enough to melt solid rock. To study it, astronomers use the James Webb Space Telescope. By waiting for the planet to pass in front of its star, the telescope captures how the starlight filters through the planet's atmospheric perimeter. Researchers initially modeled rocky planets in these extreme orbits, assuming they would be wrapped in thick atmospheres made of heavy carbon monoxide or carbon dioxide. This is a comparative chart showing the expected atmospheric gases versus the actual readings. Instead of heavy carbon compounds, the James Webb data revealed a huge spike in hydrogen mixed with only small amounts of carbon dioxide. To understand why, we look at the redox state, the chemical balance between oxygen and hydrogen deep inside. On 55 Cancri E, data indicates a chemical imbalance inside the molten core, heavily favoring hydrogen. That internal imbalance doesn't stay trapped. The immense heat of the magma ocean causes constant volcanic outgassing. Hydrogen and other gases bubble up and escape into the sky, cooling enough to form temporary atmospheric clouds before the stellar wind blows them away. The atmosphere we detect with our telescopes is a direct translation of the planet's hidden interior. The unseeable magma core is actively writing its chemical makeup into the visible sky above it. Whether it's the glowing friction of an accretion disk or the outgassed clouds of a lava world, the underlying mechanic is the same. The environment outside is reacting violently to the hidden forces inside. These boundary layers are the physical output of the systems they enclose. When we observe the rotation of a disk or the chemistry of an atmosphere, we are seeing the internal logic of the core projected outward. Just a few decades ago, astronomers were largely limited to theorizing about these extreme environments, using pen, paper, and indirect math. Today, they are actively analyzing the specific physical and chemical compositions of these objects. This leap is driven entirely by the deployment of advanced observatories and highly sophisticated indirect detection methods. We've built tools specifically designed to capture the faint echoes escaping from the most hostile regions of space. Because of this expanding dataset, lava worlds and event horizons have moved out of the realm of mathematical curiosity. They are now rigorously measured environments. The universe protects its most extreme physical states behind absolute darkness and blinding heat. But by closely examining the chaotic borders where those extremes meet the rest of space, we are finally peering inside.